Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue looking at earthquakes and the Earth's interior. So in this video we're going to be focusing on where do most earthquakes occur, and this is going to correspond to section 12.3 of your textbook. Now, as we've already discussed, earthquakes are typically produced in response to two main geologic processes. The first one is fault movement, which is of course the result of tectonic stresses trying to move blocks of rock past each other. The other major cause of earthquake activity is magma movement, and this can either be in the form of magma simply moving through the crust, so moving through dikes and sills for instance, or it could be the result of magma being erupted onto the surface of the earth via volcanoes. So the first question is, well, where do we find these two processes occurring? Do we either individually or together? Well, the most obvious answer is of course along plate boundaries. So at plate boundaries, we typically have very large pieces of crust trying to move past each other, then or bang into each other or move away from each other. So there's typically quite a lot of tectonic stresses in those environments. And we also have a situation where a lot of these plate boundaries also have the capacity to generate magma. And so we also have magma movement at some plate boundaries. And so this is obviously going to mean that plate boundaries are going to be a prime location for earthquake activity. So if we look at the picture here, you can see we have a diagram. So we obviously have Europe, Asia, Africa, and India, Australia down here. And we can see that all of these circles represent the location of an earthquake. Now, we can see straight away that the vast majority of earthquake activity is associated with plate boundaries, which are marked out here as these black lines. And that's not really a big surprise because, once again, plate boundaries are where we're going to find the highest tectonic stresses and very often the largest amounts of magma being produced. So earthquake activity in those areas is not a huge surprise. Now, what we can also see in this diagram, though, is that earthquake activity varies with depth. So we can see that the vast majority of earthquakes here are yellow circles, and so these are classified as shallow earthquakes, and they occur between 0 and 70 kilometers in depth. Now, the thing we need to remember is that the Earth's surface consists of two different types of crust, continental and oceanic. Now, oceanic crust is typically quite thin, normally somewhere between 5 and 10 kilometers in thickness. It averages about 6.5 to 7 kilometers thick. Continental crust, on the other hand, has a larger range. It can be anywhere between about 25 and 70 kilometers thick, and it will average somewhere about 35 to 40 kilometers. So straight away, this means that the vast majority of earthquake activity is due to fault movement in the crust, and it's due to magma movement in the crust. So it's no surprise that most earthquakes are going to be shallow, because continental crust is a maximum and a real upper limit of 70 kilometers thick. So most earthquake generation is going to take place in the crust, and so it's naturally going to be quite shallow by geologic standards. And so it doesn't really surprise us that most of these circles are yellow. Now, another thing you'll notice though is that not all these circles are yellow. We also have some green ones and some red ones. So the green ones are intermediate depth earthquakes, and these are occurring between 70 and 300 kilometers. And we also have deep earthquakes in red, which are occurring at depths in excess of 300 kilometers. So the obvious question is, well, what's going on to produce these earthquakes? Bearing in mind, as we've just discussed, we know that the vast majority of earthquake activity is due to either fault movement and magma movement in the crust. So where are these deeper earthquakes coming from? Well, if we look at the location of these deeper earthquakes, we will see that they are associated with subduction zones. So we have a subduction zone running along here, so that's the Aleutian Trench. We have a subduction zone running down here, a subduction zone here, there, and also coming along here and down here towards New Zealand. So we know that these are areas of active subduction, and we know that at these subduction zones we have a piece of oceanic crust which is being pushed down into the Earth's interior, down into the mantle. So obviously this helps to explain why we see these deeper earthquakes associated with convergent plate boundaries, because it's the piece of oceanic crust moving down into the Earth's interior that are causing these earthquakes. So the next question is, well, why are these earthquakes occurring in response to this piece of oceanic crust being pushed down into the Earth's interior? Well, there's three main reasons. The first reason is the most straightforward. We are trying to push a solid piece of oceanic crust through a relatively solid mantle. And so obviously there's going to be lots of friction. And so the movement between these two very large pieces of rock is going to produce lots of mechanical energy, which is going to be released in the form of seismic waves. Another thing that can happen to produce earthquakes is that the oceanic crust, as it subducts down into the mantle, can begin to fall to pieces. So you have to remember that our piece of oceanic crust is, being pushed down into an environment, and it's being forced to flex as it drops down. So once again, think of a plastic ruler. If you start to bend it, you can bend it, you can bend it, you can bend it, but at a point you're going to push the ruler too far, and your plastic ruler is going to snap. And so the same thing can happen to oceanic crust. As it dives down into the mantle, if the angle at which it's going down into the mantle steadily changes over time, well, that can start to put parts of the oceanic crust under more and more stress, and eventually they can literally snap. And of course, this breakup of the oceanic crust can lead to earthquakes being produced. Now, the final cause of earthquake activity due to subduction is a little bit more complicated to understand, and it's due to changes in minerals. So as we know, the piece of oceanic crust is going down into the mantle and the temperature and pressure is getting higher. So we know this is going to cause metamorphism, because as the minerals which were stable at the surface get pushed into higher and higher and higher pressure environments, the temperature and pressure in these new environments is going to force them to metamorphose into minerals which are stable at the higher pressures and temperatures. And so this change in the mineralogy is going to also produce a change in volume. Most minerals that form under high pressures and temperatures, like the Earth's mantle, are often quite dense. That means the atoms which make them up are more tightly packed than a mineral that's forming on the surface of the Earth where the pressure and temperature is lower. So this means that as your piece of oceanic crust goes down into the mantle and metamorphoses to produce new minerals, the new minerals that are being produced take up less space than the original minerals that made up the oceanic crust. And so, for want of a better way of describing it, your piece of oceanic crust is getting thinner because the minerals are changing. And so this change in the mineralogy obviously changes the dimensions of your piece of oceanic crust as it subducts, but it also means that as your piece of oceanic crust gets thinner, it means you're essentially going to open up some empty space. And in geology, you can't really have empty space. It's got to be filled by something. And so rocks will have to move into the empty space to fill it up. And so once again, we have rocks moving. This is going to release mechanical energy, and so we're going to detect this in the form of earthquakes. So subduction zones are going to be the focus of these intermediate and deep earthquakes, because we have this piece of oceanic crust diving down into the mantle. So let's look at the diagram, and let's look at some of the environments in which we see quite a lot of earthquake activity. Well, the first environment where we see lots of earthquake activity are at mid-ocean ridges. So these are oceanic divergent plate boundaries. Now, we know the crust in these areas is naturally quite thin. Oceanic crust is normally about 6.5 kilometers in thickness, but at these mid-ocean ridges, the crust has been stretched, so it's even thinner. So the thickness of the crust in these areas could be anywhere between 2 and 3 kilometers. And so this obviously means the vast majority of earthquake activity is going to be shallow, because once again, we know most of the earthquakes produced are going to be in response to fault movement and magma movement. There's no subduction, so that means there's going to be no intermediate or deep earthquakes at these divergent plate boundaries. Now, obviously, we know that we're going to have lots of normal faults forming at these mid-ocean ridges because they are the result of extension. The crust is being stretched. And we know the type of fault that forms in response to the crust being extended are normal faults. And so that's where the fault movement and the associated earthquakes are going to be produced. We also know that underneath these mid-ocean ridges, we have large amounts of magma being generated through decompression melting. And so this means we have a perfect situation where we have lots of fault movement due to the normal faults, and we have lots of magma moving through the crust. And so this is obviously going to lead to large amounts of earthquake activity along these mid-ocean ridges. And of course, because the crust is so thin, this earthquake activity is going to be shallow. Now, in terms of the strength of the type of earthquakes that we see, on the whole, they aren't as strong as in other locations. So most mid-ocean ridge earthquakes are not, by geologic standards, that powerful. They're often quite weak. We also find lots of earthquake activity associated with transform boundaries. So obviously this is when pieces of crust are moving past each other. They're not going up or down relative to each other. Nothing's being subducted. The crust isn't being pulled apart, so it's not under extension. We are dealing with a shear process. So we've got pieces of crust that want to move past each other. Now, obviously, in this situation, we don't have any melting. Transform plate boundaries are not associated with magma generation. So when it comes to transform plate boundaries, the earthquakes that we see are going to be the result of fault movement only. So obviously, where are the earthquakes going to be produced? Well, they're going to be produced on the fault plains. And so it's not really a huge surprise that because we have these two pieces of rock moving past each other, number one, the earthquakes once again are going to be shallow, because there's no subduction. And number two, in this case, the earthquakes can actually be quite powerful because these pieces of crust will lock into each other, and as we know, they're going to undergo stick-slip behavior. So the fault will lock, the stresses will build up over time, and then eventually, once the amount of stored energy becomes high enough, it will overcome friction and the fault will move, releasing that energy in one large event. So typically, earthquakes associated with transform plate boundaries can actually be quite large. As we've discussed, we get earthquake activity associated with subduction zones. So most of the earthquake activity is going to be shallow because it's going to be due to these pieces of crust moving past each other. So we know there's going to be lots of friction. But we also know that because of the pressure, the compressional force of these two pieces of rock banging into each other, it's also going to lead to lots and lots of faulting and folding of the two pieces of crust which are hitting one another. And so once again, this buckling of the crust and this faulting of the crust is going to produce lots of opportunities for earthquakes to be generated. Now, we've already discussed about why at subduction zones we have also we have intermediate and deep earthquakes as well, and of course this is in response to the piece of subducting oceanic crust. We can also see here we have lots of earthquake activity associated with continental collisions. So this is a continent-continent convergent plate boundary. So we have India smashing into Asia. So we've got two pieces of continental crust, and we know that continental crust is naturally quite buoyant. It will not subduct, and so when these two pieces of crust go smashing into each other, neither will subduct, and they'll just plow headlong into each other. Now, this obviously means that because there's no subduction, we aren't going to be getting intermediate or deep earthquakes. And so the vast majority of earthquake activity you can see here is shallow. Now, this is obviously because we've got two pieces of crust banging into each other, and so the crust in this area is going to be full of faults, and there's also going to be lots of folding taking place in response to the tectonic forces, and so this is going to lead to the generation of lots of earthquake activity, especially due to fault movement. Now, you will notice that there are a few areas where we do have deeper earthquakes, and the reason for this is that once upon a time, this boundary here was actually an ocean-continent convergent boundary. So there was some subduction taking place. So India, once upon a time, was all the way down here, and then it started moving northwards, mostly in the Cretaceous. So as it moves northwards, in between India and Asia, there was seafloor, oceanic crust, and that oceanic crust obviously had to be subducted and destroyed in order to allow India to move northwards. And so that meant for a while this plate boundary here was an ocean-continent convergent plate boundary, and so we had a piece of oceanic crust which was being subducted down underneath Asia. Eventually, of course, all that oceanic crust was subducted, and India eventually makes contact with Asia, producing the Himalayas. Now, we can still detect some of the signals of this piece of oceanic crust as it goes deeper into the mantle, because it's still there. It's not being completely destroyed yet. It's still subducting. And so we can see some of these intermediate depth earthquakes, and some of those are going to be associated with the oceanic crust that's still heading down into the Earth's mantle underneath Asia in this area. So that helps to explain to some degree why we do see some deeper earthquakes associated with the continent-continent collision, which is the Himalayan collision. Now, we also have some earthquakes associated with the interior of some continents. Now, the reasons for these earthquakes are variable. So some of them, for instance, are going to be due to hotspots. So we know a hotspot is a location where we have a mantle plume stuck underneath the Earth's crust, and it's going to produce large amounts of magma. And of course, this magma is going to move through the Earth's crust, and as it moves through the Earth's crust, it's going to produce small earthquakes. And so it's not really a huge surprise that we get some earthquake activity associated with areas where we have hotspots, Hawaii being a classic example of this. Now, there are also a couple of other reasons why we could have earthquake activity in the interior of a continent well away from the plate boundaries. Now, in the case of these earthquakes here, these are due to rifting. So this is the East African Rift Valley. And the East African Rift Valley is essentially trying to pull Somalia off the eastern side of Africa and move it into the Indian Ocean. And so this area here, picked out by this line of earthquakes there, and this line of earthquakes here, are actively under extension. The crust is being stretched. And so obviously this means we're going to get normal faults forming underneath the continental divergent boundary. We're also going to get magma produced through decompression melting. And so we're going to have earthquake activity due to fault movement along normal faults. And we're going to have earthquake activity associated with magma movement. And so this helps to explain why we have earthquake activity associated with this rift valley here, even though it's clearly a long way from any plate boundary. And the reason for that is it's trying to become a plate boundary, but it hasn't quite done it yet. If this process is allowed to continue, Somalia, parts of Kenya, will eventually rift off the eastern side of Africa and move off as their own little microcontinent. And of course, at that point, we're going to have a fully fledged divergent plate boundary forming. Now, another reason why we can have earthquakes occurring within the interior of continents is due to orogenic events that happened in the past. So, for instance, this line of earthquake activity that we can see here is actually focused along an old convergent event. So once upon a time there was an ocean-continent collision, a continent-continent collision, which occurred along this line approximately here. And so this produced a set of mountains, similar to the Himalayas or the Andes, for instance. And so once again, this is obviously going to lead to the crust in this area becoming absolutely stuffed with faults. Now, the mountain range itself has pretty much been completely eroded away. Remember, this event happened a long time ago. However, the faults which were produced by this mountain range's formation are still present in the crust. And so every once in a while, one of these faults will move, producing an earthquake. So this helps to explain why we do see some earthquake activity in areas of continents where we would otherwise not expect it to be there. And that's simply because we have fault movement along pre-existing faults which were formed by earlier tectonic processes. So now we're going to look at North and South America. So we can see on the whole, the trends which we are seeing here are similar to what we just saw on the western side of the Pacific. So where are earthquakes in this area? Well, once again, we can see we have lots of earthquake activity associated with these mid-ocean ridges, these divergent plate boundaries. Because once again, we've got lots of crustal extension producing normal faults, and we have lots of magma generation through decompression melting. So we have fault movement and magma movement. So that means lots of earthquake activity, although on the whole, the earthquakes produced will typically be relatively weak. Now, we also have earthquake activity associated with subduction. So this, of course, is the Andean subduction zone right here. And we can see we have lots of shallow earthquake activity, but we also have intermediate and deep earthquake activity, which, of course, is associated with the piece of subducting oceanic crust as it subducts from the east to the west. So the piece of oceanic crust is subducting downwards and it's getting deeper as it moves eastwards. And so this helps to explain why the earthquakes are getting deeper as we move from west to east, because that is what's happening to the piece of oceanic crust being subducted. It's getting further and further down into the mantle as it moves towards the east. We of course also have earthquakes associated with transform plate boundaries, as we've discussed. So this is going to be where we have strike slip faults, and so we've got pieces of rock that want to move past each other. Now remember, transform plate boundaries are not associated with magma generation, so we're not going to see any kind of volcanic activity associated with these transform plate boundaries, but we are going to see plenty of earthquake activity associated with fault movements, and these are going to be strike slip faults. And transform plate boundaries, like the reverse and thrust faults formed at convergent plate boundaries, are typically going to be capable of producing some quite powerful earthquakes. So very often transform plate boundaries and faults associated with convergent plate boundaries are very often quite dangerous places to live, because there is a risk of stronger earthquake activity occurring. And of course, just like we saw when we were looking in the previous slide, there's also some earthquake activity associated with the continental interior. So if we look over here, we can see here's the classic example of earthquake activity well away from a plate boundary. Of course, Hawaii, we know this is a hot spot. We know there's lots of magma movement occurring in this area. So of course, this helps to explain why we can see all of this earthquake activity right here. Now, in terms of North America itself, you will see there's lots and lots of relatively isolated earthquake activity. These are going to be in response to pre-existing faults. So, of course, as you can see, there's a general trend there. It's not strong, but it's present. And of course, we know this is the trend of the Appalachian Mountains. And so we know the Appalachian Mountains were forming in the Carboniferous and the Permian, so we know that these were forming some 350 million years ago. So the mountain range that formed at that time, of course, has been eroded away, and what's left behind are the faults which were produced by that orogenic event. And so even though the mountain range is on the whole pretty much gone, it's been lost, the faults which were produced are still present in some of the rocks, and so movement along these faults is going to lead to earthquake generation. All right, thank you for watching, everybody, and have a good day.